Yeah, it looks like some kind of chemistry thing.
Oh, wow.
All right, so I think we'll get started. We were talking about kind of taking dielectric materials, immersing them in some external electric field. That electric field would polarize the material, either by displacing electron clouds and neutral atoms or by rotating molecules that are already polar. So that resulted in a polarization, and we were able to define these so-called bound charges. There was a bound charge density, volume density, which was given by minus the gradient of the polarization. And there was a bound charge surface charge density, which is determined by E dot with this normal vector to the surface. And then ultimately we defined that electric displacement as essentially the sum of the electric field and the polarization. And we could write down sort of an equivalent form of Gauss's law for these types of fields. Now, we weren't able to solve too many problems with this model, because what you would need to know is you need to be given the polarization in order to make progress and finding, like, say, total electric fields. What we're going to do today is we're going to talk about linear dielectrics, and in that case, we are going to be able to solve some problems. So in fact, we'll do a little bit of work on defining what we mean by linear dielectrics, but then most of today's class will be kind of just working through some examples and some applications. So for electric fields that are not too strong, for many materials, we find that the polarization is just proportional to the electric field. And I mean, I think if you think about it a little bit, that probably makes a bit of intuitive sense. So let's imagine that we take some material like a sheet of Teflon or whatever, and we put it in a weak electric field. It's going to start to polarize some of the atoms in there, but at the same time, that sort of arrangement, that order of, say, positive charges along the top surface where the electric field's pointing up, and then negative charges along that bottom surface, that's competing with thermal energy. And the thermal energy tends to randomize everything. As I turn up the electric field, I start to overwhelm that thermal energy. And as I keep going up and up and up, then I get basically my entire material is as polarized as it gets. I've completely overwhelmed that thermal motion, and I'm as polarized as I get. And if I keep turning up the electric field, I don't get more polarized. So that's sort of how I intuitively think about it. So we're thinking of the case where we haven't completely overwhelmed that thermal randomness that's in the system. Okay, so when P is proportional to E, we have a proportionality constant that's called the susceptibility. The proportionality constant is called the electric susceptibility. A lot of what we're doing for these dielectric materials and electric fields is going to translate to magnetic materials and magnetic fields. So we'll have a magnetic susceptibility next week. Okay, so this is the electric susceptibility, and so this is the Greek letter chi. So what we do is we say the polarization is equal to epsilon naught chi times E. The reason that we, I guess it's not actually quite true what I said. The proportionality constant is the product of susceptibility and epsilon naught. The reason that they pull out epsilon naught here is just to make the susceptibility dimensionless. It has no units. So chi E is unitless. It's just a number. Okay, so I'm gonna call this equation star because we will refer to it a few times, I think. So the susceptibility is just a material property. You could go look up tables for different materials and read off its value. So chi E is a material property, and it could also be, say, temperature dependent. How hot or cold is your slab of Teflon? And materials that obey star are called linear dielectrics. You can see that this is going to resolve our problem of not being able to calculate electric fields without knowing the polarization, because now we can just say the electric field is proportional to that polarization, and we'll be able to make some progress. We'll see some examples of that today. Okay, so we're going to focus today entirely on these so-called linear dielectric materials. Let's just emphasize, we've talked before about we apply an external field that causes the polarization. The polarized material creates its own electric field. Here, the E in equation star is the total electric field due to both whatever externally applied field you came up with, plus however the polarization modified that field. So let's note that E in star is the total electric field. Maybe I should say total electric field. So it's that which causes the polarization plus the contribution from the polarized material. All right. So what we could do is we could plug equation star into our electric displacement. So remember that was defined to be epsilon naught times E plus this polarization, which is going to become epsilon naught E plus, well, okay, where was equation star? It's going to be epsilon naught chi times E, which we can then write as epsilon naught 1 plus chi E times the electric field, like so. Okay, so for linear dielectrics, then this result tells us that not only is the polarization proportional to E, this electric displacement is also proportional to E. Okay, so I should emphasize that not all materials are linear dielectrics. There are some materials for which you can have like a frozen in polarization. So even in the absence of an electric field, an applied electric field, you could still have some alignment of your dipoles in that material. And these would not obey the sort of stuff that we're going to talk about today. All right. Now, for better or for worse, there are a bunch of definitions that are sort of equivalent, but a little bit different. So let's just list what they are. The quantity epsilon naught 1 plus the susceptibility is called the permittivity of the material. It's called the permittivity of the material. And epsilon r, which is the permittivity divided by the vacuum permittivity is called the relative permittivity. Or sometimes the dielectric constant.
That way it's called permittivity of free space when you don't have a chi-e.
Yep, that's right. Griffiths, if you read Griffiths, he doesn't like that. And he doesn't like it because it seems to imply that vacuum could be also polarized, but there's no charge or there's nothing in vacuum to polarize. But yes, that is true. It's the vacuum space. This is the vacuum permittivity because chi e would be 0. Yeah. I'm going to go off on just like a little 1-minute tangent here. In a later chapter in Griffiths, if you take 401, you'll find that the susceptibility and the permittivity can be complex quantities. And so let's imagine that you had an electric field that was oscillating at some frequency. Then your little polar molecules or your neutral atoms would have to constantly switch their, let's think of the polar molecules, it's easier to think about. They're rotating, right? They're actually physically rotating in that oscillating electric field. If that electric field is slow, they have an easy time keeping up. But if you increase the frequency, they have to rotate faster and faster, and eventually they'll start to lag behind. And if, for those of you that are in Physics 331, right at the beginning of term, we talked about complex quantities and what they physically represent. And they physically represent, when you have imaginary components, is a phase delay. And so the rotation of these polar molecules starts to lag behind the rotation or the changing direction of the electric field. And not only that, you start to get dissipation and you get heat generated. So when you microwave your food, what you're doing is you're exposing the polar water molecules or ice molecules in your frozen food to an electric field that's oscillating at, it's like 2.45 gigahertz, so 2.45 billion times a second. And the polar molecules can't keep up with that. There's some dissipation, and it's that dissipation that heats your food. In fact, the peak in the dissipation for water is not at 2.45 gigahertz, but it's way up at like closer to 20 gigahertz. And so you might think, if I had my microwave operate at 20 gigahertz, I would heat my food faster. Unfortunately, what happens is that the depth that the fields penetrate into your food is also frequency dependent. And as you go higher in frequency, the depth that they penetrate gets more shallow and shallower and shallower. So if you did it at high frequency at 20 gigahertz, you would end up with a scalding hot surface on your food with a frozen center. And you know, you already get that sometimes anyways, right? So this 2.45 gigahertz that they've chosen is a compromise between how deep the fields penetrate into your food and how much dissipation you get when you apply those fields. So anyways, that's some of the stuff that you might encounter in a course like Physics 401. All right, so let's start with an example. A conducting sphere has charge Q and is surrounded by a linear dielectric of permittivity epsilon. Okay, and so what we're going to try to do is we're going to try to find the potential at the center. Okay, so let's draw it. I learned a new trick in Notability. We'll see if it works. Here we go, circle. Sweet. So then we're going to surround that with another one, and I think I can get it to center. All right, good. So what we're going to do is we're going to say that our conducting sphere has radius A, and it carries charge Q because it's a conductor. That charge is on the surface. And then our dielectric is this blue thing, and it has an outer radius of B. All right, so what do we know? We know that there's a Gauss's law version for the electric displacement, and it's just equal to whatever the free charge is. And so what we're going to do is we're going to choose, say, a Gaussian surface that is, bigger than radius A. And it doesn't matter if it's bigger than A or it's bigger than A and B, because the dielectric can only have bound charge. And this Gauss's law depends only on the free charge. Okay, so we can pick a Gaussian surface. It's going to be a sphere with radius R bigger than A. All right, so the integral of d dot dA is just going to be d times the surface area of that Gaussian surface, and Q free is just going to be Q. This is the charge on the conductor. All right, so fair enough. So that just has to be equal to Q. And so right away, we get that D is equal to Q over 4 pi R squared. And if we wanted to, we could say that's going to be in the radial direction. last time we would basically be stuck here because unless somebody told us about the polarization, we couldn't really go further. However, if we have a linear dielectric, we can go further. So for, okay, actually, let's just say, therefore, D, which is epsilon naught E plus the polarization is equal to, well, let's see. It's going to be epsilon naught E plus, and let's look at our polarization. It was equation star, wasn't it? It was epsilon naught times the susceptibility times E. So epsilon naught times the susceptibility times E. And that's going to have to be equal to Q, the charge on the sphere. So we could simplify this. We could say epsilon naught 1 plus the susceptibility times E is equal to Q. Sorry, I forgot my 4 pi r squared r hat, right? 4 pi r squared r hat. Here we go. And so this thing here is just our permittivity, right? Susceptibility is 0, we would recover the vacuum permittivity. Okay, and so therefore, what we find is E is just equal to Q over 4 pi. Now this is epsilon instead of epsilon naught divided by r squared r hat. If we have a position where we're inside the dielectric, so R is between A and B, then we have this exact result. Sorry, it's muscle memory puts a little knot at the end of my epsilon. If we're at a radius bigger than B, then epsilon is just equal to epsilon naught, and we recover the usual results. This permittivity is bigger than the free space permittivity. And so that means the electric field inside our dielectric is a little less. And that makes sense because what we would get on our dielectric is if this free charge Q is positive, then it's going to polarize our dielectric material such that the negative would be near the inner radius of our dielectric, and we'd get positive on the outer part. And so there would be an electric field due to the polarized material that points inwards and partially cancels with the electric field that's due to the charged sphere. And so dielectrics tend to reduce the electric field inside their own, inside that material. But outside, if I did a regular Gauss's law, you know, all that matters is the total enclosed charge. But the bound charges are going to completely cancel, and so they contribute nothing to the electric field outside. Outside is only due to the electric field from the charge on the conductor. And that's in fact exactly what we found right here. Okay, good. So the original question was not to find the electric field, it was to find the potential at the center of the sphere where R equals 0. So we know that, delta V, the change in potential, and I'm going to choose to find the change in potential between infinity and 0 is going to be minus the integral of E dot dl from 0 to infinity. Now, by convention, we usually say the potential at infinity is zero unless our charged object happens to extend out to infinity. It doesn't in this case, so we'll call this zero. And so therefore that means we have V0 is equal to the integral from 0 to infinity of E dot dl. We have to do this as a piecewise integral because we have two different electric fields well, in fact, we have three different electric fields. What's the electric field inside the conductor? Zero. So we have to do this in three little bits. And so this would be the integral from 0 to a. In principle, we would have a term like this, but the electric field is going to be 0 in our conductor, plus the integral from a to b of, so what are we going to have in that case? We're going to have the version where the permittivity is epsilon instead of epsilon naught. So we would have q over 4 pi epsilon r squared. And then our dl would just be a dr. And then we'd have to integrate from b to infinity of q over 4 pi epsilon naught r squared dr. Okay, so what this becomes is there's some common factors here, q over 4 pi, integral from a to b of, let's see, the integral of 1 over r squared is going to be minus 1 over r, isn't it? So it's going to be minus 1 over r. We have a factor of epsilon, and we're going to evaluate that between a and b. And then we're going to have minus 1 over r, factor of epsilon naught, and that's going to be from b to infinity. So let's see, what do we get? Q over 4 pi. At b, we'd get minus 1 over epsilon b plus 1 over epsilon a. And then we would get, let's see, minus 1 over epsilon divided by infinity, which is 0, plus 1 over epsilon naught b. And I think that's correct. Is it right? It looks like it. Okay. So there it is. That's the potential at the center of the sphere. Just by way of review, what would be the potential at the surface of the conducting sphere at r equals a? The potential inside a conductor is not 0, but constant. Yeah. So everywhere inside the conductor, that must be the potential. Okay. So let's just jump right into another example. I want to find the electric field between the plates of a capacitor that has been filled with a linear dielectric. All right, so we're going to have a capacitor plate. Should be able to copy this. All right. All right, good. And I'm going to fill it with a dielectric material, and we'll give this dielectric material some susceptibility chi e. We'll say that these plates are separated by some distance d, and then maybe they're connected to some battery so that they charge up. So we'll put some positive charge on the top plate and some negative charge on the bottom plate. All right. So what's going to happen is we're going to get some polarization P that points downward. So the positive ends of the dipoles will be attracted to the negative plate, and the negative ends to the positive plate. Okay, so we're gonna do this Gauss's law problem again, using the electric displacement. So that has to be equal to the free charge. So what I want to imagine is choosing a Gaussian surface that's a little pillbox, and I'm gonna draw it like this. So it's gonna straddle, say, the top plate. And so we'll say that what we have here is some area A. And then there's like a bottom surface to this little box, and we'll be worried about that as well. So we know that the electric fields are going to be vertical in the capacitor, and it's going to be 0 outside. So we're pretty sure that we should find E equals 0 outside and E not equal 0 inside. If our capacitor has charge per unit area sigma on the plates, like plus sigma on one plate and minus sigma on the other, then the amount of free charge that's enclosed by our green Gaussian surface is just going to be sigma times whatever that area is. Okay, so let's see. This E dot dA around our box. Our box technically has 6 sides, but 4 of those sides have normal vectors that are perpendicular to the electric field between the plates of the capacitor. And so they're not going to contribute anything to Gauss's law. It's only the top and bottom surfaces that matter. And so we would have, if we imagine that we have an electric field inside our plate, then our n hat for the top plate is pointing up, and the n hat for the bottom plate is pointing down. And so one of them is parallel to the electric field, and the other is anti-parallel. So we could, if we wanted to, write this as, let's see, d times the area of the top plate, and I'll put a minus sign because those are going to be anti-parallel, plus d times the area of the bottom plate. But we've already argued that outside, we're not expecting to see anything. The electric field's 0, there's no dielectric outside, so there can't be any polarization. So that's fine. And then this would just have to be equal to sigma times A. All right. So let's say this is D in and say that this is D out. All right, so D in, which is equal to epsilon times E, let's just worry about magnitudes for now. So therefore, we have epsilon E times the area. I shouldn't have put these subscripts. The top and bottom areas are the same. So we'll say this is the top of our Gaussian surface, and this is the bottom of our Gaussian surface. That has to be equal to sigma times A. And so therefore, E is going to be equal to, well, let's see, the areas cancel, and this would be sigma over epsilon. So what I want to do is I want to rewrite this in a more convenient form, a form that will hopefully be more recognizable. Sigma is charge per unit area. So it's going to be Q divided by A for sigma. This this permittivity could be written as a product of the dielectric constant and the free space permittivity. And so that's all true. Now, if you know E and you know the plates are separated by a distance D, what's the voltage difference across the plates? It's either going to be times D or minus divide by D. Which one is it? Try again. So delta V is the integral of E dot DL. So it has to be E times some length. And so the voltage difference across the plates is E times D, which is going to be Q D epsilon R epsilon naught times A. All right. I'm going to rearrange this to be Q over delta V, which is the definition of capacitance. So if we solve for Q divided by delta V, it's going to be epsilon R epsilon naught A divide by D. What is epsilon naught A over D? That's the capacitance when we have nothing between the plates, some air between the plates of a capacitor. And so this is the capacitance with nothing between the plates. And so therefore, C is equal to epsilon R C naught. And presumably this is something that you've seen before at some point. When you stick a dielectric between the plates of your capacitor, you enhance the capacitance. So you're able to store more charge for a fixed voltage. And so if you're trying to make a large capacitor, you make plates with a large area, but then you put a dielectric that has a large relative permittivity or a large dielectric constant between those plates. Okay, so the capacitance is enhanced by a factor of the dielectric constant.
Capacitance is like how much energy a capacitor can store.
It's how much charge you store for a fixed voltage. So if you connect a battery across your plates, you've got some fixed voltage. How much charge is going to reside on that?
And then with the dielectric, you can put more charge.
Yeah. Yeah.
And but it's stored in the unit.
No, this would be the charge that actually goes on the plates. Yeah, so you know the bound charge in the dielectric, you in a practical sense you don't really care about because you know I can't use that to, I don't know, do something in a circuit or something. So the one way to think of it is if you have this bound charge, then it's going to attract extra charge of the opposite sign. And so that's where the extra stored charge comes from. It's attracted to the bound charge that's in the dielectric. Yeah. Okay, so let's do another example. So let's find the capacitance of a parallel plate capacitor that's partially filled with dielectric epsilon 1 and partially filled with a second dielectric epsilon 2. All right, so here, I think. All right, so what we'll do is let me paste another one. Come on, go, something like that. All right, so what we'll do is we will make this one dielectric epsilon 1 and this one dielectric epsilon 2. And I'm going to make this distance here x times d, and I'll make this distance here 1 minus x times d, where x is some number that's between 0 and 1. Okay, we'll put some, say, positive charge on the top plate, and we'll put some negative charge on the bottom plate. Well, from the problem that we just did, we found that the electric field in the dielectric is sigma divided by whatever that dielectric constant is. And so what we could do is we could right away write down from the previous problem we know that the electric field in the first dielectric is going to be sigma over epsilon 1, and the electric field in the second dielectric will be sigma over epsilon 2. You know, if you wanted to, you could just do Gauss's law with the electric displacement at this bottom plate, and then do it again at the top plate, and you'll get these results exactly like we just did. All right. So I'm going to calculate the potential difference across our capacitor. So it's E dot dl with a minus sign. I don't really care about the minus sign for this problem, but we're going to go from 0 to x times d. I guess I have a weird axis here where I'm going to call the top of the top plate is 0, and then we're going to go to x times d by moving down, and so that will be E1 dot dl, and then we have to go from xd to d, and in that region we have E2, and so we have to do this E2 dot dl integral. Okay, but the electric fields are going to be constant in these materials. So these are easy integrals. This is just going to be E1 times xd. But E1 is sigma over epsilon 1 xd. And then we have sigma over epsilon 2. And then what are we going to have? We're going to have d minus xd. And so that's the same as 1 minus x times d. All right. So delta V is equal to minus sigma is charge per unit area. So it's qxd over epsilon 1 times A. In fact, let me write epsilon 1 as the dielectric constant times the permittivity of space. And then we have minus q, the dielectric constant, times permittivity of free space, A. And then we have 1 minus x times d. All right. Like we did last time, we could say we know that C0, if there was no dielectrics at all, would be epsilon naught A over D. But I've got that in both these expressions. So our delta V is going to be equal to, let's see, Q over C naught. Let's take the minus sign out. And so what's left over? We have x over epsilon r1 at plus 1 minus x over epsilon r2. I think that's everything. Let's see, that looks right. We could rewrite this in let's say a more convenient form. This is the same thing as x epsilon r2 plus 1 minus x epsilon r1 divided by epsilon r1 epsilon r2. Okay, and so what I'm going to do is I'm going to try to calculate the capacitance just like we did in the last problem. I'm going to say C is, I don't care about the minus sign, C is Q over the voltage difference across our capacitor plates. So let's see, it's going to be equal to, what do we have? C0, and then we just have to invert this thing. So it's epsilon R1, epsilon R2, epsilon R1, 1 minus x plus epsilon R2 times x. There's a couple things that are worth noticing here. One is this expression is like calculating a series combination of capacitors. If I have capacitors in series, the equivalent capacitance is 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And so this, if I divide by Q, delta V over Q, that's 1 over C. And then I have 1 over C naught times that dielectric constant is like 1 over C1. And then I have 1 over C naught times the second dielectric constant is like 1 over C2. So effectively, we have a set of series capacitors. Okay, we could check if our answer makes sense. Check. There's a few things we could check. One, if x is equal to 1, that would mean we filled the entire capacitor with the first dielectric epsilon 1. And so what happens? If x equals 1, this term in the denominator goes away. We divide by epsilon r2, we get C0 epsilon r1. That makes sense, right? We get C is equal to epsilon r1 times C0. That's good. 2, sorry? So this would just become a 1. Yeah, that's right. Yeah, exactly. If we put x equals 0, this term's going to vanish. We'll get just a 1 here. We divide by epsilon r1, and we have just epsilon r2. So x equals 0 corresponds to the entire capacitor filled with the second dielectric. And the third possibility is if we make both dielectric constants equal to 1, what happens? We're going to get 1 here and 1 here. So we'll have 1 minus x plus x. It's just 1. This is 1 and 1. We're just going to get C0. And so it's like we have no dielectric in our capacitor at all. And so all this result makes good sense. All right. How are we doing time-wise? We have about 30 minutes. All right. Example. Let's see, what do I want to do? Okay, I think this is reasonable. So let's find the charge density induced on a linear dielectric that fills the space at z is less than 0 when a point charge q is at z equals d. Okay, so let's draw the picture. I'll draw the picture on the next page here. So we're going to have this will correspond to our dielectric is going to live in this space here. And so there's some permittivity epsilon. And then we're going to place a charge Q. Let's see, I can move this down. I'm going to place a charge Q. We'll say it's positive over here, and this is a height d above this plane. And so this plane sits at z equals 0. All right. So what would we expect to happen? We would expect to see that our dielectric is going to become polarized. The negative ends of these polar molecules or atoms will be attracted to the positive charge. And there's going to be, presumably, a higher concentration of these negative charges directly below where the plus Q is. And so that charge density should spread out, should get weaker as we move away from that position. All right. So that's what we think will happen. Let's see what our calculation shows us. So first, let's consider the possibility of a bound charge density per, like a volume charge density. So that would be equal to minus the gradient of the polarization. Now, for our linear dielectrics, the polarization is proportional to E. Okay, so therefore rho B is going to be minus, let's see, epsilon naught times the susceptibility times the gradient of E. Sorry, it's not the gradient of E, it's the divergence. Sorry. The divergence of E, we know is from Gauss's law, is the total charge density, which includes the bound charge and the free charge divided by epsilon naught. All right, so then we have this kind of funny situation where we've got the bound charge density on both sides. However, we can solve for that. And so let's see, rho B is going to be equal to, the epsilon naughts are going to cancel. So it's going to be minus the susceptibility times the bound charge density minus the susceptibility times the free charge density. And if you go and solve for the bound charge density, it would be minus chi E 1 plus chi E times the free charge. So this actually isn't relevant to our problem because our dielectric has no free charge. The only free charge is this point charge, which is outside of the dielectric. So in this case, we would find that rho B would be equal to 0. But this is a useful result for potentially other types of problems. But in our problem, there is no free charge in the dielectric. Therefore, rho B is equal to 0. All right. So that leaves us with just the surface charge density. And so that is going to be calculated from the dot product with a normal vector. And our normal vector is pointing in the z direction. So this is just equal to z hat in our case. Okay, good. So sigma b is the polarization times n hat. That's just the z component of the polarization. But for linear dielectrics, this is proportional to the electric field, and it's the total electric field. It's the contribution from external fields, in this case, the field due to our point charge, plus the contribution due to the bound charge itself. And so we'll have to figure out both those contributions. So this is epsilon naught times the susceptibility times the Z component of the electric field that's sitting right at the surface of our dielectric. And so this is at Z equals 0. And I want to emphasize that this is just inside the dielectric. Okay, so what we need to do is we need to find E at some arbitrary point at the dielectric surface. There are two contributions. One from the point charge Q, and one from the bound charge at sigma B. All right. So we'll start with the contribution from Q. So I'm going to try my best to draw like a 3D version of this picture. So here's the surface of our dielectric. You know, it continues, it fills the half space below Z equals 0. And then we have Q sitting up here. This is our distance D. And then I'm going to try to go to some arbitrary point on the surface of this dielectric that sits over here. And I'm going to call this, this is the distance R. And this is the distance, well, yeah, I guess I should, well, okay. We're going to be worried about this hypotenuse, and here's theta. This distance is d squared plus r squared square root is that distance there. Okay, so the electric field contribution from Q. If Q is a positive charge, which we said it was, then it's going to make an electric field that is in this kind of direction. But if we go back here, we said we only wanted the Z component of that electric field. And so the Z component is going to be something like this, EZ, and this is that angle theta, and this is equal to E cos theta. So I want to know what cosine theta is, and from the upper black triangle, cosine theta is the adjacent side D divided by the hypotenuse. So we'll just make a note of cos theta is D over r squared plus d squared. Okay, good. So for our point charge, we know how to calculate electric fields from point charges, 1 over 4 pi epsilon naught Q over the square of the distance. And if we want just the Z component, it's going to be 1 over 4 pi epsilon naught Q over the square of the distance, which is d squared plus r squared, times the cosine of theta, which is d square root of r squared plus d squared. Okay, and we'll put a minus sign because that's pointing down into the dielectric. So this is equal to minus qd over 4 pi epsilon naught, and then it's d squared plus r squared to the 3/2 power. All right, so that's one of the contributions to our electric field. The second one is from sigma B. Let's see, from sigma B. Let's go back to this picture here. And so we have this negative bound charge sitting right at that surface. And so inside the dielectric, we would have a contribution that would be pointing upward. So there'd be some kind of like E due to sigma would be pointing up along positive z direction. But we've done this kind of problem before where you have a surface charge, like capacitor plates. The electric field between a capacitor is sigma over epsilon naught. So you get sigma over 2 epsilon naught contributions from the top plate and from the bottom plate, and then they add up and that factor of 1/2 cancels. Here, we don't have 2 charge plates, we just have a single plate. And so the magnitude of this electric field is the surface charge density sigma divided by 2, and instead of epsilon naught, it'll be epsilon. Okay. Sorry, for some reason I have epsilon naught. I guess I see. It's because we're calculating the electric field that is just outside. That's, well, I don't know. I'm a little confused right now, but let's just go ahead with this. So E sigma is going to be minus sigma B over 2 epsilon naught. We'll go with epsilon naught for now. I have a minus sign here, but remember, we're expecting this charge density to be negative. So minus sigma is a positive number, which corresponds to that electric field pointing upwards. So this is overall positive because sigma B is negative. Okay. So what we want to do is we want to combine all of this stuff together. Sigma B is epsilon naught times the susceptibility. Oh, you know what? I guess because we already have this factor up here, maybe that's why. But anyways, we have the total electric field in the z direction. It's the sum of the electric field from the point charge and the electric field from the bound charge. Okay. So sigma B is equal to epsilon naught times the susceptibility. And then we have from the point charge, there's 4 pi epsilon naught, and then I think it was d squared plus r squared to the 3/2 power. Okay, and then we had from our bound charge, the sigma over 2 epsilon naught. So solve for sigma B. Let's see. Sigma B times 1 plus the epsilon naughts are going to cancel, and we're going to get a chi over 2, I think. So chi e over 2 is equal to, let's see, it is minus qd. The epsilon naughts cancel. There's a susceptibility, and then divide by 4 pi, yeah, okay, d squared plus r squared to the 3/2 power. Let's see, this thing is equivalent to 2 plus chi over 2. So therefore, finally, sigma B is equal to minus. Let's see, the 2 is going to cancel partially with that 4. So we'll have a 1 over 2 pi. We have this factor of susceptibility divided by 1 plus, 2 plus the susceptibility. So it's 2 plus the susceptibility. And then we just have qd over d squared plus r squared to 3/2 power. And that is our bound charge. Some of the features that we were expecting. If R is equal to 0, that's where sigma is the largest, and that's right beneath the point charge. If R goes out to infinity, far away from where that point charge is, then this bound charge density goes to 0. So that all makes sense. Let's note that QB, if we wanted to find the total bound charge, we would integrate over the surface of our dielectric. So this is the total bound charge. Well, that's going to be 1 over 2 pi chi over 2 plus chi. And then we have a factor of QD, and we'd have the integral of r dr d phi. That's our dA, divided by r squared plus d squared to 3/2. This is not a hard integral to do. You could do a simple substitution. If you do that, what you're going to find is that this is equal to, I think it is, yeah, it's just 2 pi over d. And so you end up with minus the susceptibility over 2 plus the susceptibility times q. Now, this is something that we could check to see if it makes sense. If the susceptibility is 0, susceptibility is a good name, right? It's how susceptible is your material to becoming polarized. If it's 0, it can't be polarized at all. We would expect no charge. And if I put a 0 here, QB is going to be 0. That makes sense. If the susceptibility is really large, so our material is very susceptible to being polarized, then we're going to get a large number divided by a large number. This is going to approach 1, and we get minus q. And so it's, in that sense, it's a bit like the conductor, where we get the charge that exactly cancels the charge that's sitting above it. All right. So I'm not going to do any more calculations. I want to just show you one other thing that is kind of interesting about these dielectrics. And it's all we have to do is just analyze a simple picture. So 4.4.4 forces on dielectrics. All right. So what I want to imagine is that we have a capacitor. And so I'm going to try to draw this to the best of my ability. We'll put positive charge on the top plate and negative charge on the bottom plate. But what I'm going to do is I'm going to put a dielectric, I'm going to put a dielectric partially inside this capacitor. Maybe the dielectric fits inside the plates, but it's been pulled out a little bit. And so here's my bottom plate goes to here. All right. So this is a dielectric partially inside a capacitor. Well, what's going to happen is that the part that is inside between the plates will become polarized. And so we'll end up with some surface charge that's bound here. So some negative surface charge here, and some positive surface charge here. And so these are our sigma B's. All right. Well, if we were to draw the electric fields of our capacitor, it's going to point from the positive plate to the negative plate. And if that's all we did, if we assumed that the electric field between the plates of our capacitor is they're just perfectly straight, and then once we get outside the capacitor, they're zero, then there would be nothing to think about here. It would just sit like this and nothing would happen. But that's not actually the case. Whenever you get close to the edges of the capacitor, you're going to get these fringing fields. And these fringing fields kind of spread out, and they do some kind of funny shapes like so, like that. And what I'm going to be interested in are what are the shapes of these fields close to our bound charges. So in fact, what we could do is we could say, well, whoops, over here at this bound charge, this bound negative charge, that fringing electric field is something like this, right? It has that direction. It's going to have a component that is parallel to the surface of the dielectric and a component that's perpendicular. I don't really care about the perpendicular component. I'm going to care about the parallel component. So this is E parallel. So if this parallel component is interacting with this part of the bound charge, it's going to exert a force on it. That force will be into the capacitor because this is where our negative bound charge is. And so we have a force that tends to push that dielectric into the capacitor plates. We could play the same game over here. I could say, well, I've got some positive bound charge over here, and in this case, my electric field from that fringing contribution looks something like this. And I can again find the parallel component of that electric field. Parallel. And it's going to exert a force on this bound charge, and it's going to push the dielectric inside the capacitor plates. And so this is F.
Why is that force in the same direction? Oh,
Because it's a positive bound charge. Yeah, that's right. Yeah, yeah. So the parallel components of the fringing fields push the dielectric into the capacitor. Now, what you might think is that's going to be a very difficult calculation because I'd have to know the shapes and magnitudes of these fringing fields. And that's true. Calculating the fringing fields is very difficult. But Griffiths goes through a little argument where you can actually calculate these forces. And the way you do it is we did the example where we had two different dielectrics between the plates. So we had a plate, one dielectric, a second dielectric, and a bottom plate. And that looked like a series combination of capacitors. Here, if you like, we have part of our capacitor with just vacuum. And so if you like, that's like a dielectric with a dielectric constant of 1. And then you have some other dielectric here. And this you can treat as parallel capacitors, and those capacitors just add. And if you do an analysis of the energy of that capacitor, you can actually work out the force that the dielectric gets pulled in. the argument is that if I displace this a little bit, I pull it a little bit out, I do work on the system. And I could calculate how much work I do. And the force is equal to the derivative of the work. And then you can write the work as the energy in terms of the capacitance, but we can write down an expression of the capacitance, and so we can take that derivative and find. Okay, so if you're interested in that, that is in Griffiths, and it's not a long calculation, but it's a pretty neat result. Okay, all right, so that's where I'm going to stop. And what we'll do next week is we'll do magnetic fields and materials, and a lot of the stuff that we talked about. We'll have a parallel version in magnetic fields. So instead of polarization and electric dipoles, we'll have magnetic dipoles, which can be rotated in external magnetic fields. We'll talk about magnetic susceptibility. Yeah.
Question of the course.
Yeah.
I decided not to include this stuff on the final because it sounds like we're going over quite a bit of stuff. Like this week.
Oh, I don't know. I didn't want to give the impression that I was racing through material just to get it done so that I could ask you questions. That's the reason. And the other reason is I think we've covered quite a lot of material without this stuff included. But at the same time, I want you to see this, and I'm going to tell Alex that I covered everything. He should expect that you've seen all this stuff when you do. Yeah. All right, sweet. Thank you very much, everyone. Have a good weekend.